Alright, here we are once more. And what we are going to do is we are going to play the next levels. There's 4 that we can choose from: delay, RAM, shift, hex racer. And I guess the first thing we are going to do is play the RAM level. I guess this is a level where we are going to add a RAM to our CPU, add a RAM block, so the computer can can address 256 additional bytes of memory. You need a way to decide which of the 256 bytes inside the RAM we are addressing. Select the register and wire it up, so its value always selects the RAM address. When you later want to load or save to the RAM, you will have to first copy the RAM address to this register. Okay. In this test, first copy from input 32 times and store these values. After you've loaded the 32 values, output them in the same order as you got them. Outputting before you have read all the inputs will fail the level. Alright, 32 times, right? So, which register are we going to choose? So far we have 16 that we've wired up, right? No, we actually have 32. We could solve this level by now without using the RAM component at all, which is interesting, if you ask me. So, alright. The RAM component. Actually, maybe what we want is a 3-way MUX at this point. Because wait a second, how is this out of RAM blocks? So the computer can address 256 additional bytes. You need a way to decide which of the 256 bytes inside the RAM we are addressing. Select the register and wire it up so its value selects the RAM address. Alright. We're going to, maybe we can look it up here, right? This is load save address. Oh, and by the way, we're already in a position, I just realized, where we can choose more than 8-bit when we are talking about the RAM. When we're using the RAM. And I was talking about this earlier, when we've built our register, that CPUs might not only run on 8-bit, so bytes, but also 16 or 32-bit. So, which one are we going to choose? I guess we're going to go with 16. And let's choose the white color for this. Let's let our RAM sit right here. This is going to select our address, and this seems to be our address bit, address input. Interestingly enough, we only have one save and one load bit. But we have 4 values and 4 outputs. So I guess we can split. And I guess these are going to be consecutive bytes. I'm actually not sure. All right. So now we have wired up our register to the RAM. So, right. When you later want to load or save to the RAM, you will have to first copy the RAM register. Yes, okay. Okay, we are very free on how we will on how we can implement this, right? Well, basically no rules that we have to follow in this case. And I mean, we can use 16 in our opcode. So in case the 16 is active, we would be able to save respectively load, and it is going to be valuable. Well, I guess we're going to use the 8 as well. We don't have to, though. We don't have to. And there are definitely better solutions for this. I know this because I've already built better solutions for this. Question is, do we actually build the better solution, like implement it right now? Because we are going to have to build it later on. There will be no way around this. I guess maybe we actually want to use our more like an additional register. And the reason for that is we will then have the ability to use the value that is given to us by the RAM, either as argument 1, as argument 2, or result address, right? So this register is holding. No, we would still have to modify it, have to be able to modify it. In case like read from it and write to it. This gives us more freedom when thinking about this, when programming it later on. So I guess the question becomes right now, do we, by the way, load is gonna use an OR gate. Because it can either be argument 1, wait a second, why is it giving us a star? I have no idea. So this would be number 32, right? No, 31. Going to do the same for this. Which means that and this has to also activate the switches so we can feed the value into our machine. And we can just connect it like this. Alright, so now our RAM has become somewhat like an additional register that we can use within our circuits, but only when using the value that is stored in it as a argument, but we want to be able to also write to it, right? So this is going to be implemented the same way. So now we have it all wired up. This is basically it. This is all there is to it. I still kind of wish it was sitting more like up there. Now we can actually start to define our own instructions, and this is the moment where the fun begins, right? Because this is the moment where we actually implement assembler code, right? Because this is what assembler actually is. We have an architecture that looks, in our case, like this. And we've built it from the ground up. Isn't that amazing? And, oops, this is the wrong button. Assembler instructions are actually architecture specific instructions that correspond directly to bit and byte codes. So I guess we're basically at it. The point where we should be able to understand what an assembler actually is and how it works in this specific architecture. So first of all, we have the immediates, right? Is that correct? Yes, it actually is. Look, no matter what, these two will always be immediate, right? Or do we actually want it like this? We only have to care about the opcode, by the way. We only have to care about the opcode. Do we actually want to define it like this? I guess so, yes. So the next part is that, see, we've built an immediate level, right? We've built it, and we could have defined it back then. And instead of defining everything right now, we've built this circuit that lets us immediate argument 1, respectively argument 2, and use it as arguments for our ILU. And therefore these two most significant bits, which is what we define right here as a rule, will define if we immediate one of the arguments. So U, our condition mode, let's call it cond. Now we are going to define the next instruction. Right, this is cond. Let's keep it like this, because in case we're in condition mode, no, actually we don't want this. Or do we? Yes, I guess we do. Because once you're online, Yes. You three define our conditions. The moment you're offline, we're basically in calculate mode, right? Let's see how this plays out. Now we can basically pull up our screenshots. I don't know if this is a good idea, to be honest, but now we are going to do it like this. if we make a mistake, this is it's not going to be that bad, even though we are going to put in a little bit of work right now. So we would have to make it a little bit like this. You are equal, right? Equal, if equal. Copy it 6 times. 1, 2, 3, 4, 5, 6. And now this one is not equal. This one is less. This one is less or equal. This one is greater. Okay, now we're missing one. Can we move this down? Let's just trash it and copy this one. You would be, you're greater, and you are greater equal. We can actually have a look at how these instructions are defined within ARM. So we can actually use the correct or corresponding commands. Let's see if I can find it. No, I'm gonna look it up and show it to you next level, right? And oh no, I don't want to. I didn't mean to add, because I don't know if we can. We will be able to modify these later on, right? It's not like they're going to be set in stone. So this is calculate mode. This one defines calculate mode. And we can basically only be in conditional calculate mode. So let's keep it like this for now. Put up our next screenshot. The screenshot in which we defined or rather the screenshot in which we can see 3, 4, 5, 6. Yes, this is correct. Which add sub and or not XOR add sub and or not XOR. And as we can see, I mean, this and this still undefined. And we can later even extend it to this extent, where we would be able to, did I delete too many? No, I didn't. We would be able to add a lot more conditions, respectively, potential calculations. This is not entirely true, because later on we are going to use this one, use this bit as well, to be able to, yeah, I'm not going to talk about this too much right now, because we will get to this later. So now we basically have created an instruction set that will enable us to program this thing. This thing. We basically have created our own little assembler language. I'll put this one away. So what is it that we wanted to do? We now have to import them. Actually, I don't know. Actually started building a little compiler for this architecture on my GitHub. If you're interested in that, maybe you can have a look at this. It's written in C. And yeah, later on we will also have a component that lets us import text files, where we can actually write our own code using the language that we defined and import it straight into the game, which is amazing, if you ask me. So I guess immediate 1, immediate 2, immediate 1, 2, not sure if we are going to need this. It is what it is. Also, I don't know if the manual shows this. No, it actually doesn't, but what we can do is we can actually, let me show this to you. We have immediate 1, right? And we have immediate 2. And we have immediate 1, 2, right? Which are basically the possible combinations of these two bits. But we could also, this is basically equal to immediate 1 plus immediate 2, because this is going to basically OR which is not exactly true. These two, it's basically, I don't know, it's going to stack them on top of each other. Yes, it's going to OR them. It's basically going to OR them. OR them together. So these two instructions would be equal, right? You can use this plus to just OR them together, and that is why we actually don't exactly have to use this definition at all. We're going to see how we want to program this thing. Just define it in case we want it. So now define calc condition. This is condition mode. This is calc mode. I guess we could now start to define our registers. One. No, this is our 0. R1 is this one. Oh, I made a mistake. Just realized. Calculate is correct, but con does not. This is con. It is basically mirrored. And that means, because this is 128, right? That means that a lot of the instructions that we just defined are wrongly defined. This is how it has to look like. Oh, this is so unfortunate. Made an effort. To build this. Okay, see now, I just realized that we definitely had a mistake in this as well. Why is it that this is condition mode? 1 equals 1. Oh, this is horrible. This is all mixed up. It's all mixed up now. Let's see what happens if we close this and open it again. At the end of the day, we're going to have to do this. But yes, I guess I'm going to do this off camera and end the video for now. And next time just show you what we did. Go to waste. Anyways, goodbye. I hope you had fun. I hope you took away something from this. Yeah, goodbye.